Unit gravitation exercise questions. First question: you can shield a charge from electric forces by putting it inside a hollow conductor. Can you shield a body from the gravitational influence nearby matter by putting it inside a hollow sphere or by some other means? So the question indicates in such a way that if we have a positive charge here inside a metal chamber, then you cannot observe any field produced by this positive charge outside. You can take a point outside. If it is a metal chamber, you cannot see the field of this positive charge outside. That means the field of this charge can be shielded with the help of metal chamber. And the question here, we can have an object of mass here kept inside a chamber. Then can you observe gravitational force due to this mass at this point? The simple way we can speak in such a way that do we experience any gravitational force of Earth when we are inside a closed chamber? Of course, we do. So the same way here you can see, by keeping the mass inside a metal chamber, in a closed chamber, you cannot shield gravitational force. Electrostatic force you can shield with the help of a metal chamber, but you cannot shield gravitational force. You can observe gravitational field at this point. So answer is no. It is not possible to shield the object from gravitational force by keeping it inside a closed chamber. Then next, an astronaut inside a small spaceship orbiting around the Earth cannot detect gravity. If the space station orbiting around the Earth has a large size, can he hope to detect gravity? Okay, here we need to understand one point. That take the case of Sun and Earth. With respect to Sun, Earth is a freely falling object. And already we have seen a freely falling object does not experience gravitational force. Its net weight is 0. So we do not have any gravitational force because of Sun. But we have the gravitational force due to Earth. So the same comparison you can use here also. Space station is freely falling. So the station and the payload do not experience any gravitational force due to Earth. But the astronaut inside the spaceship will experience gravitational force due to spaceship. Because with respect to spaceship, the astronaut is not freely falling. So there will be gravitational force due to the space station. So answer is yes. There is no gravitational force, or we can say the astronaut does not experience any gravitational force due to Earth. Our spaceship is freely falling, but you will experience gravitational force due to spaceship. Then next, if you compare gravitational force on Earth due to the Sun to that due to the Moon, you would find that the Sun's pull is greater than the Moon's pull. However, the tidal effect of the Moon's pull is greater than the tidal effect of Sun. Why? The simple answer is Moon is close to Earth. And in certain cases, when we speak when the distance distance is very large, it is found that the gravitational force varies in the order of 1 by r cube also. So if it varies in the order of 1 by r cube, then you can see the strength of the force falls very fast. Therefore, if the object is far, far away, then we can say the effect of gravitational force will be much less. So therefore, the influence of moon is comparatively greater than the effect of sun. Then next, choose the correct alternative. Acceleration due to gravity decreases with increasing altitude. Acceleration due to gravity decreases with increasing depth. Then acceleration due to gravity is independent of mass of the body. Then next, the formula minus gmm by r, the same only 1 by r2 minus 1 by r1, the formula we have derived is more reliable formula. This is the reason I have mentioned. That is, we have a clear reference point for this formula compared to the formula mgh. This formula is just mgh. The height difference is r2 minus r1. Okay, then next we have question 4. Details are given. The orbital time period is given 1.769 days. So we can convert it into seconds. Then radius of the orbit is given. Then you are asked to find mass of the Jupiter. So how can I find mass of the Jupiter? We use this formula. T is equal to 2 pi into under root r cube by gm. Under root r cube by gm. Square this equation. Then cross multiply. You will get m is equal to g t square. So when you cross multiply, m is equal to 4 pi square r cube divided by g t square. Now substitute the values. You can find the value of m. And you are asked to prove that it is about 1/10 of mass of the sun. Mass of the sun is, solar mass is around, mass of sun is approximately 2 into 10 power 30 kilogram. 2 into 10 power 30 kilogram. And you will get the mass here, the answer, around 1/10 of 2 into 10 power 30 kilogram. 2 into 10 power 30 kilogram. Now, next, question 5. So here, the mass of the galaxy, total mass of the galaxy is given. It is around 2.5 into 10 power 11 times the mass of sun. And the distance is given from the galactic center is around 50,000 light year. So the total mass you can convert. Okay, 2.5 into 10 power 11 times of solar mass means total mass is 2.5 into 10 power 11 into 2 into 10 power 36. So that is around 5 into 10 power 41 kilogram is the total mass. Then the distance is 50,000 light year. Light year you have to convert into meter. Okay, 50,000 into 9.46 into 10 power 15 meter. Then afterwards we can use the same formula which we have used in the previous problem. So we have a time period t is equal to 2 pi into under root r cube by gm, under root r cube by gm. So here you need to calculate only time period. So substitute the values in SI unit, you can calculate the value of time period. Then question 6, choose the correct alternative. If the zero of potential energy is at infinity, the total energy of an orbiting satellite is the negative of kinetic energy. Then part B, the energy required to launch an orbiting satellite out of Earth's gravitational influence is more or less than the energy required to project a stationary object at the same height out of Earth's influence. Of course, it is less. Then, next, question 7. Does the escape speed of a body from the Earth depend on mass of the body? No. Then, the location from where it is projected? No. Location in the sense you have to take a like equator or poles, etc. Then, the direction of projection? No. Then the height of the location. Of course, it depends on height of location. Because escape velocity formula, V is equal to under root 2 gm by r. Under root 2 gm by r. And if it is projected from a height, then the equation becomes under root V is equal to under root 2 gm divided by r plus h. So we can say as the height changes from the surface of Earth, the escape velocity also changes. So it depends on the height of the location. Then next, question 8. A comet orbits the sun in a highly elliptical orbit. Does the comet have a constant? What are the quantities remains constant? That is what we have to see here. Okay, linear speed is not a constant. You know that it is elliptical orbit. When it is close to the sun, its speed increases. Angular speed also, angular momentum. Angular momentum, as there is no external torque there, the angular momentum is conserved. Then kinetic energy, no, according to the distance changes. The kinetic energy and potential energy will change, but the total energy remains constant. Whenever the kinetic energy increases, the potential energy decreases, so that the total energy remains constant. So two quantities are constant: angular momentum and total energy. Then question 9. Which of the following symptoms is likely to afflict the astronaut in space? Swollen feet, swollen face, headache, and orientational problem. You know that in space there is no gravitational force. As there is no gravitational force, there is no gravitational pull downward. The blood has a tendency to reach in our brain. Okay, so in such a situation, as more blood is reaching the brain, there is a possibility of swollen face because more blood is moving upwards. So you can have headache because of the same reason, and also you may have the orientational problem also. Next, question 10. The gravitational intensity at the center of a hemispherical shell of uniform mass density as the direction indicated by arrow. So here the diagram is given. The first question, this question is about this object placed at the center. This is a hemispherical body. It is completely filled with the matter. It's not hollow. Okay. Now, in which case, what will be the direction of net gravitational force on a small object placed at this point, capital C? That's the question. Now, we can see here the gravitational attraction in various directions. And when you place an object at C here, that will be attracted towards left by the matter here, and similarly attracted towards right also. So in this way it will be attracted here also. All these attractions are mutually cancelled. But you know, being a hemispherical body, no matter is in the upper part. Therefore, in all the way it will be attracted downwards. So the net attraction will be along the direction indicated by C. Because in the upper part it is vacant. Okay, so there is no mass in the upper part. All other sideways and all other region, we can observe the mass. So as there is no mass upward, there is a net force acting downward. So option C is the correct option. Then question 11 is a continuation. For the above problem, the direction of the gravitational intensity at an arbitrary point P, this is the case, point P is indicated by the arrow. So which case it is? Point C. So point C also, when you observe, you can see attraction towards G and attraction towards D will be cancelled. Then the attraction towards right hand side and attraction towards left hand side will be cancelled. So we can say here we have more mass, but distance is also large. Here we have less mass, but distance is less. So that also will be cancelled. So from the left side region, the attractive force will be strong as distance is less. So therefore, when you take all these attractions, the net attraction will be again acting downward only in the direction of indicated by E. Okay, the case of the shell we have seen, wherever you place, the net force will be zero. Wherever inside the shell. The same aspect here you have to take. When the distance is large, mass is also large. When distance is less, mass is also less. So those forces are also get cancelled, so that the resultant force, just like what we have seen in the previous question at the center, the same way here also, the net force is acting normally downward. So option 2 is the correct answer. Now next, a rocket is fired from the earth towards the sun. Now the data is given: mass of sun, mass of earth, then orbital radius. Now at what distance from the earth's surface, earth's center, the gravitational force on the rocket is zero? That is the question. So here we can take sun, then can have earth, and the rocket is sent from earth to sun. And here you can take an arbitrary point here where the rocket of mass small m is there. Earth has mass me, we can take, and sun has mass ms. Now from earth, suppose the distance is x up to this point, and the remaining distance will be r minus x, where r is the radius of earth's orbit around the sun. Now at this point we can take the net force on the rocket is 0. Why is it so? Because the attraction from Earth and the attraction from Sun both are equal on this rocket of mass m. So in this situation the net force will be 0. So accordingly the gravitational force between the rocket and the Sun, G ms m divided by r minus x the whole square, is equal to the gravitational force between Earth and the rocket, G MEM divided by x square. Now G, small m, etc. will be cancelled. You can cross multiply the equation, simplify, and you can find the value of x. Rest of the quantities are given there. Find the value of x, then you will get the distance between the null point where net gravitational force is 0 on the rocket and from the center of Earth. Now, next question 30. How will you weigh the Sun? That is, estimate its mass. The mean orbital radius of Earth around the Sun is 1.5 into 10 power 8 kilometer. So radius of the Earth orbit is given. Then the time period of Earth around the Sun is 1 year. You can convert it into seconds. Value of G also, and here also. So you need to use the formula G is equal to 2 pi into under root Gm. This is mass of Sun you have to take. Sorry. Under root R cube by Gm. And this M is mass of Sun. How can you calculate the mass of Sun? Square this equation. After squaring this equation, you will get mass of Sun ms is equal to 4 pi square R cube divided by G T square. So substituting the values, you will get the answer. Now, next question 50. Question 14 you need not study. Question 15. A body weighs 63 Newton on the surface of the Earth. What is the gravitational force on it due to the Earth at a height equal to half of the radius of Earth? Okay, the question is related to the variation of G with respect to height. So we have G dash is equal to G into R square divided by R plus H the whole square. R plus H the whole square. Now both sides of the equation you can multiply by M because force is given there. Mg dash is equal to, now it is weight, Mg into R square divided by R square divided by R plus, it is given H, H is half of the radius, so R by 2 the whole square. Now take LCM inside the bracket, simplify the equation. So you will get this is equal to 4 by 9 mg. Mg is given in the question. It is 63 Newton. Substitute mg there as 63, so that mg dash you can calculate. Now next question 16. How much would a body weigh halfway down to the center of the earth if it weighed 250 Newton on its surface? Again, the question is about depth. So we can have again you can take the formula g dash is equal to g into 1 minus d by r. Here also both sides of the equation you can multiply by m. So mg dash is equal to mg into 1 minus depth is given half of the radius of r. So r by 2 divided by r. Now mg is given 250 Newton. R will be cancelled. So substitute the values, and so you will get mg by 2. Substitute the value of mg and find the value of mg dash. Next, question 17. A rocket is fired vertically with a speed of 5 km per second, 100 km per second. Then, from the Earth's surface, how far from the Earth does the rocket go before returning to Earth? The data is given: mass of Earth, radius of Earth, etc. So here, the rocket is fired from the Earth's surface. When it is fired from the Earth's surface, okay, so what are the energies possessed by the rocket? The total initial energy. The rocket will have kinetic energy, half mv square, and it will have potential energy minus gmm by r. Minus gmm by r. Then, when the rocket reaches the maximum height, afterwards it falls down. At the highest point, it has no kinetic energy, it has only potential energy. Therefore, E final is equal to minus gmm divided by r plus h, where h is the height attained from the surface of Earth. Now, apply the law of conservation of energy. EI is equal to EF. Total initial energy is equal to total final energy. Total initial energy is equal to total final energy. So that you get an equation for the rocket, that is half mv square minus gmm by r is equal to minus gmm divided by r plus h. Now all small m's are cancelled there. Then you can substitute all values. After substituting the values, first you can find the value of r plus h. Once you get the value of r plus h, substitute the value of r there and h can be calculated. Now, next question 18. The escape speed of a projectile on the Earth's surface is 11.2 km per second. A body is projected out with thrice this speed. What is the speed of the body far away from the Earth? Ignore the presence of other objects. So here, the body is projected with a velocity Vi, we can take. So its initial energy, okay, is equal to half mvi square is the initial kinetic energy. And this initial kinetic energy, okay, that this kinetic energy is used for all purpose. One is it has to escape from Earth gravitational attraction, for which the object has to spend a kinetic energy corresponding to escape velocity v. So an energy half mv square is used to escape, and the remaining energy is retained by the object, that we can take as half m vf square, where vf is the final velocity after escaping from the gravitation attraction. So you will get an equation. The total initial kinetic energy is equal to the kinetic energy to escape plus the final kinetic energy. Now you can simplify the equation. All half m's are cancelled there. So you will get vi square is equal to v square plus vf square. Now the relation between vi and ve is given there. So we need to calculate vf. Vf is equal to under root vi square minus v square. Therefore, vf is equal to under root vi is 3 times escape velocity, the whole square, minus v square is equal to under root 8 v square. Now substitute the value of v, we can take outside. 8 means it is 2 root 2 into v. Substitute the values, you will get the equation, sorry, the value of final velocity. Now next, question 19. A satellite orbits the Earth at a height of 400 kilometer, convert into meter. How much energy must be expended to rocket the satellite out of the Earth's gravitational influence? Mass of the satellite is given, then mass of Earth is given, then radius of Earth is given, g also. So we know that the satellite can escape from gravitational attraction of Earth provided its total kinetic and total energy. So kinetic energy, total energy must be 0. So we can calculate the total energy of the satellite at present. We have the total energy formula. Total energy of a satellite, we have the formula minus gm, capital M is mass of Earth, into m mass of the satellite, divided by 2 into r plus h, 2 into r plus h. So substitute the values and find the total energy of the satellite at present. So you will get the answer around minus 5.9 into 10 power 9 joule. Now this is the total energy at present, and we know the total energy must be 0 so that the satellite can escape. So how much energy you need to supply to make the total energy 0? You need to supply an energy which is equal to plus 5.9 into 10 power 9 joule. So that the total energy at present plus energy supplied, when you add together, you will get a total energy 0. Once the total energy is 0, the satellite can escape. Now, next question 20. Two stars, each of 1 solar mass. So each star is having mass 2 into 10 power 30 kilogram, are approaching each other for a head-on collision when they are at a distance 10 power 9 kilometer. At a distance 10 power 9 kilometer, which means 10 power 12 meter. That time their speeds are negligible, which means when the stars are at 10 power 9 kilometer away, their speeds are negligible, their kinetic energy is 0. What is the speed with which they collide? The radius of each star is given 10 power 4 kilometer. Okay, so we can take the situation like this. So we have two stars, both are having mass m, and they are at a distance r apart. That time their kinetic energy is 0, which means they have only potential energy. So how much is the initial energy? Initial energy EI is equal to minus G m m. Remember both the m's are same, so it becomes m square divided by r. That is the initial potential energy, and there is no kinetic energy. Kinetic energy is 0 there. Then afterwards, these two stars collide. When they collide, like this, when they collide, the distance between the centers of the star is 2r, 2 times their radius. Radius is given already, 10 power 7 meter. So what is the final energy? As the stars are in motion, they have kinetic energy. So we can take 2 into half m v square, because both are having kinetic energy. Half m v square is the kinetic energy of one of the stars. For two stars, we have 2 into half m v square, minus they have potential energy also because their centers are at a distance 2r. So we have minus g m divided by 2r. Then again here also we can apply the law of conservation of energy. Total initial energy is equal to total final energy. So you will get a minus g m square by small r is equal to m v square, 2 and 2 here cancel, minus g m square divided by 2r. 1 m will be cancelled throughout. Then afterwards you are asked to calculate with what velocity they collide. Simplify this equation and find the value of v. All quantities are given there. Find the value of v, the velocity with which they collide. Then next question 21. Two heavy spheres of mass 100 kilogram each, radius 0.1 meter, it is shown in the diagram. They are 1 meter apart, they are centers. Okay. What is the gravitational force and potential at the midpoint of the line joining the centers? That means point X. We need to calculate gravitational potential and gravitational force. Okay. So you can see, suppose when we assume another object is placed at the midpoint. Okay. You can just imagine an object of mass small m is placed at the point X. Then this object of mass m is equally attracted by both the spheres. Therefore, what is the force? Net force at the point X. Net force is 0. Because attraction due to both the spheres on either side will be equal. So net force is 0. Then next, gravitational potential at the midpoint. So there will be gravitational potential due to both the spheres at the midpoint. Therefore, the total gravitational potential V is equal to 2 into potential due to both the spheres, 2 into minus gm divided by r. And what is the value of r? R, you have to take the distance from the centers of the sphere. So you have to take 0.5 meter value of r. So substitute the values, you will get the value of gravitational potential at the point X. Now, next, is an object be placed at that point in equilibrium? If so, is the equilibrium is stable or unstable? So what is the meaning equilibrium condition? We have seen, okay, in the chapter rotation, what is the meaning of equilibrium? So you place the object at point X. We have seen net force acting on the object is 0. Therefore, we can say the object is at equilibrium. The net force is 0. There is no possibility of torque also. So that we can say, because you can see here, the line of action of both the forces are same. As the lines of action are same, there is no possibility of torque. Torque is 0, force is 0. Therefore, we can say the object placed at that point X is at equilibrium. So answer is yes. The object at the null point is at equilibrium. Now again, if so, if the object is at equilibrium, is the equilibrium stable or unstable? So what is the meaning of stable equilibrium or unstable equilibrium? We know that at point X, the object is at equilibrium, force is 0. Now, if you displace that object from X, left or right, we can say, then release it. If the object returns back to that point, then we say the object is in stable equilibrium. If it does not return back, then we say it is in unstable equilibrium, which means from the equilibrium condition, if you just disturb the object, then the object will move away from there. Afterwards, it is not going to come back. In such a situation, the equilibrium is said to be unstable. Now let's analyze what happens here. Okay, suppose you move this object M close to the sphere in the left hand side. Suppose the object is now placed at this point, object M. What will happen? The attraction between left sphere and the object will increase, while the attraction between right sphere and the object will decrease. As the attraction is stronger towards left hand side, the object will move towards left hand side. which means it is not going to come back to the point X. As the object cannot come back to the point X towards the equilibrium position, we say the equilibrium is unstable equilibrium. Okay, so understand clearly what is the meaning of stable equilibrium and unstable equilibrium. When the object is at equilibrium condition, when it is being disturbed, if the object returns back to the equilibrium position, then that equilibrium is known as stable equilibrium. If the object cannot return back to the equilibrium position, then the equilibrium is unstable equilibrium. So in this case, we have seen the object cannot come back to the equilibrium point X. Therefore, the equilibrium, of course, the object is at equilibrium, but its equilibrium is unstable. Now, come to the additional exercise. So here again, we can have a satellite 36,000 kilometers from the surface of Earth. Then, what is the potential due to Earth's gravity at the site of the satellite? Now, mass of Earth is given, radius is given. Okay, so gravitational potential formula V is equal to minus Gm divided by R plus H. Over here, M is mass of Earth. Gravitational potential at a height 36,000 kilometers is asked, so H we substitute as 36,000 kilometers, so that you can calculate directly the value of gravitational potential at that height. Next, question 23. A star 2.5 times the mass of the Sun, is 2.5 into 2 into 10 power 30, and collapsed to a size of 12 kilometers. Rotates with a speed of 1.2 revolution per second. Revolution per second means it is frequency. Now, will an object placed on its equator remain stuck to its surface due to gravity? Okay, so we have the star and an object is placed on the surface of the star. And when the star rotates, we know this object is already placed on its surface will have a circular motion when the star rotates about its axis. Now, you can see the radius is given. Now, under what condition the object remains stuck? When the star rotates about its axis, the object we have seen it is in circular motion. Circular motion needs centripetal force. And here the gravitational force between the star and the object will give the necessary centripetal force for the object. So gravitational force gives centripetal force. Gravitational force gives the necessary centripetal force. Gravitational force you can calculate Fg is equal to Gmm by R square. You can find the value. Then small m is not given there, mass of the object. So answer you will get in terms of small m, that much Newton you will get. Now centripetal force you can calculate. Centripetal force is equal to m into mr omega square. Omega is again 4 pi square nu square. Nu is given frequency 1.2 revolution per second. So now substitute the values, find the value of centripetal force. Here also you will get the answer in terms of m, because small m is not given in the question. That much Newton. Now if gravitational force greater than centripetal force, what you have calculated here, then the gravitational force can provide the necessary centripetal force for the circular motion so that the object remains stuck there. So calculate both the values and see which one is greater. If Fg greater than Fc, the object has enough centripetal force and it remains stuck. Then next, question 24. A spaceship is stationed on Mars. Okay, here it is given a spaceship of mass small m is on Mars. How much energy must be expended on the spaceship to launch out of the solar system? Should be launched out of solar system. So we have Sun, then radius of the orbit of the Mars. Then from there we have the spaceship of mass small m. We can take ms as the mass of Sun. Now, how much energy you need to supply there? That is the question. So again, the concept is the spaceship can escape provided its total energy must be zero. So what is the total energy of the spaceship due to solar system? That is what we need to calculate there. So here the total energy formula we can use. Total energy is equal to minus G ms, mass of Sun. We know that for the entire solar system, the mass of the Sun is the influential one, and the spaceship has to escape. So into small m, mass of the spaceship we have to take, divided by 2 into, so what is the total distance? The total distance we have to take from the Sun we need to calculate. So it is Rm plus we have to take radius of the Mars, okay, as indicated here in black color, radius of the Mars. So we can write it as R, and plus h, height of the spaceship from the surface of Mars. And here it is not given compared to this distance. H we can neglect, so that you will get the formula minus gms m divided by 2 into rm plus r, and find this value, the total energy of the spaceship with respect to solar system. Now we know if total energy is zero, then the spaceship can escape. So here when you calculate total energy, present total energy of the spaceship, you will get a negative value. Once you get that negative value, again as we have done in problem 19, you need to give its positive value so that the total energy becomes zero. So whatever value you will get is, suppose you are getting negative x here, then you need to supply positive x so that the total energy is zero, so the spaceship can escape. Now, next question 25. A rocket is fired vertically from the surface of Mars with a speed 2 km per second. 20% of its initial energy is lost uh, due to Martian atmospheric resistance. How far will the rocket go from the surface of Mars before returning to it? Okay, so here again we can calculate similar problem we have seen already. Initial energy we can calculate. Initial energy is equal to half m v square minus g mm divided by r, kinetic energy plus potential energy. And final energy, when it returns back, it reaches the highest point. At the highest point, there is no kinetic energy, only potential energy. So we can have g mm divided by r plus h, where h is the height attained, maximum height attained from the surface of Mars. Now we can take it, the conservation of energy. We have total initial energy is equal to total final energy. But question says that 20% of its initial energy is lost due to Martian atmospheric resistance. So 80% of initial energy is equal to potential energy. Now substitute the values of EA and EF, these two equations, simplify and find the value of R plus H.